This video is going to give you an introduction to molecular orbital theory and hybridization of orbitals. So we can't talk about molecular orbital or MO theory without first talking about atomic orbital theory. So until the mid-1900s, atomic orbital theory, or AO theory, was the premier theory on bonding in molecules. So AO theory tells us that orbitals overlap to form bonds, and these are from spin-paired electrons. So what does that look like? So atomic orbital theory would tell us that, say we have a 1s orbital from a hydrogen, and we have another 1s orbital from a hydrogen, and we know that these form a covalent bond that are going to be H bonded to H. Atomic orbital theory says that these kind of look like a Venn diagram when they come together, where we have a spin-paired electron, where if we look, one is pointing up and one is pointing down, and such that in the bond, one is pointing up and one is pointing down. Atomic orbital theory would predict that this is how the bonding electrons and the orbitals look overall on the molecule of H2. If we look at something a little bit more complicated, let's say we have a 1s orbital from hydrogen, and then we have a 2p orbital from fluorine. Say we're making hydrofluoric acid or hydrogen fluoride. We would take these orbitals, they would overlap. We would have a 1s orbital, and then a 2p orbital would overlap, and we'd end up with HF, covalently bonded. And if we look at the electrons, we'd have one pointing up, one pointing down. They would be unpaired, but then we would pair them, and they would be spin paired in the bond. And we would have a view of bonding that looks like this. Atomic orbital theory, however, breaks down when we look at molecules like CH4. So CH4 is carbon bonded to 4 different hydrogens, and we know from Gen Chem that the geometry of CH4 is going to be tetrahedral, with the bond angle being 109.5 degrees. If we look at the electron orbital diagram of carbon, we have 1s2, 2s2, 2p2. So based on this kind of view of atomic orbital theory, methane or carbon and methane should really only form 2 bonds, but we see it forming 4 bonds. So atomic orbital theory breaks down here and can't explain why carbon forms 4 bonds, why it's tetrahedral, why it's evenly spaced, because it should, according to atomic orbital theory, only form 2 bonds, which is incorrect for a lot of organic chemistry. So more accurate than atomic orbital theory is molecular orbital theory. So molecular orbital theory, or MO theory. So this says that atomic orbitals combine to form molecular orbitals, and molecular orbitals are over the whole molecule. So as we saw, atomic orbitals are localized to the bond, but molecular orbitals are delocalized over the entire molecule, and they're usually generated computationally, but we can see that molecular orbitals are a little bit more accurate in predicting the bonding, especially when it comes to hybridization of orbitals. What we see is when 2 atomic orbitals combine, it's going to form 2 molecular orbitals. And we'll see this more in the video about molecular orbital theory and MO diagrams, but the same number of atomic orbitals will generate the same number of molecular orbitals. So let's talk again about CH4. So CH4 forms 4 bonds, and we know from Gen Chem that it's going to be because it's sp3 hybridized. But what does sp3 hybridization actually mean? So if we look at carbon, actually let me draw an energy diagram of this. So if we think about carbon, and we think about the electron, the orbital diagram for carbon, we're going to have a 2s orbital, and then we have a 2p orbital. or 2p set of orbitals. We have 2s2 and 2p2. So according to this, atomic orbital theory says that we really should only have two bonds forming, but we see in CH4 and other organic compounds that carbon forms four bonds. So we know it's sp3 hybridized, and sp3 hybridization comes from these four orbitals doing what's called mixing. So mixing of orbitals means that they combine, it's a linear combination of these orbitals, and they combine into no longer 1 and 3, but they combine into four degenerate orbitals, and this is going to be our sp3 orbitals. And our sp3 orbitals distribute those electrons evenly, and we have four electrons. So this is why carbon can form four bonds. It has four evenly distributed sp3 electrons that can form a degenerate set. Now these orbitals are going to spread. Now just like p orbitals spreading out to form a degenerate set, the sp3 orbitals are going to spread out the most they can when they are in the geometry around a particular atom. We know that four things spread out the most is going to be in a tetrahedron. And so that the bond angle is going to be 109.5. This is where the tetrahedral shape of methane comes from. If we look at specifically at an sp3 orbital, so we have an s orbital, and then we kind of overlay a p orbital where one of them is in phase and one of them is out of phase. What we end up getting is an sp3 hybridized orbital that looks something like this. We have a little bit on one side and a lot of on another side. So this is sp3. Well, we see that if it's s and 3p orbitals, it's going to be 25% s character and 75% p character. So it is largely p orbital directed, so that's why it has this shape with a little bit of s character mixed in there. So where do the other hybridizations come from? Now, the other hybridizations are similar, where there involves mixing, but it's a different amounts of orbitals mixing in each one. So let's look at sp2 and then sp. So sp2, let's look at, for instance, bf3. So the electron orbital diagram for B is 1s2, 2s2, 2p1. So if we're looking at just the orbitals of the frontier orbitals, the valence electrons of boron, we have the 2s2 and the 2p1. Boron we see is making three bonds to it. Where does this come from? And we see that one s orbital and two p orbitals are going to mix, such that you get three degenerate sp2 orbitals and one unhybridized p orbital. So we get three degenerate electrons in the sp2 and then one empty p orbital. So what does this look like physically? So if we look, we have a trigonal planar geometry, which is what the expected geometry for BF3 is. So we have F, 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 and B in the center here. And we would also have a perpendicular empty, so all of these would have one electron, which would pair with the appropriate symmetry electron from F, probably p orbitals. But then you have an empty p orbital that's going to appear vertical on that boron. This is what makes BF3 or boron-containing compounds Lewis bases. They have an empty p orbital to accept electrons, Lewis acids. We see that it adopts a trigonal planar geometry. Again, the geometry here indicates that it's 120 degrees, and that would be consistent with an sp2 hybridized center. Just to hammer this point home, let's look at sp hybridization. An example of sp hybridization would be BeF2. If we look at beryllium, we see that it has a orbital configuration of 1s2, 2s2. So its frontier orbitals, we have the 2s and then the 2p. It's 2 electrons and 2s. If we mix, we'd end up with these two orbitals mixing, so it can form two bonds instead of zero bonds. We'd have an sp hybridized orbital, and then we'd have two unhybridized p orbitals, and these would have two electrons in it. Just to note, this sp2 hybridized orbital, This is going to be 33% S and 66% P. If we look at SP, it's now 50% S and 50% P. So we're increasing the S character and decreasing the P character as we move from sp3 to sp2 to sp. So if we were looking at the bonding arrangement of an sp situation, we have B in the center. It's got two sp orbitals, and then you'd have F with the appropriate symmetry, and the orbital is probably p orbitals. So you'd have probably these p orbitals matching up with to form these bonds. You'd have spin paired electrons on either side to form a sp. Again, since it's sp, it's 180 degrees, whereas the angle in sp2 is 120 and the angle in sp3 is 109.5. Just things to note, hybrid orbitals are degenerate, meaning they are at the same energy level and they are equally preferred. So there is no preference for one over the other. They are equal in energy. And note that bonds from hybrid orbitals are stronger than those from unhybridized orbitals. So a bond formed from an sp orbital is going to be stronger than a bond formed from a strictly s or strictly p orbital. And that kind of describes hybridization overall. This is why carbon structures form such strong networks, is because we're sp3 hybridized across, and those are very, very strong bonds being formed.